In this presentation, we examine algorithms. So an algorithm is a sequence of instructions that are followed step by step to solve a problem. This does not need to be on a computer. So algorithms are all around us and we use them all the time. We often associate algorithms with computers, but this isn't so. Algorithms refer to any problem that is solved using a sequence of steps, whether or not this is on a computer. For instance, in our day-to-day routines, we often follow a set of instructions to complete a task. For instance, make a cup of tea, getting up in the morning, brushing our teeth, following a recipe, building a piece of flat pack furniture, maybe solving a math problems. So the key point is that a program runs an algorithm, but an algorithm is not only a computer program. So there are 4 algorithm constructs that I kind of want to discuss now, including sequencing, assignment, selection, and iteration. With sequencing, we are considering a set of steps that need to be performed in order to complete a task. Each line of code will have some operation, and these operations will be carried out in order line by line. Assignment is the allocation of data values to variables, constants, arrays, and other data structures so that the values can be stored. Selection represents a decision in the code according to some conditions. So if a condition is met, then the block of code is either executed or it is not. So often alternative blocks of code are executed according to some other condition. So typically in programming, selection uses if, else, and else-if constructs. And with iteration, sometimes we wish the code to repeat itself or certain subset of instructions to repeat itself until a condition is met. So we use loops such as for, while, and repeat until loops, and these are all examples of iteration. When we're presented with a complex problem, the first thing we really need to do to that problem is to try and break it down into smaller, more manageable problems that are easy to solve. This is what decomposition is. So therefore, our algorithms can therefore be more modular and therefore more intuitive, and the components of the algorithm can actually be much more simpler. Without decomposition, it could actually be too difficult to solve some complex problems. So abstraction allows us to remove unnecessary detail from a problem. So this also makes our problems easier to solve. So we use abstraction in everyday life as well as in programming. So for instance, when we're driving a car, we're not really that interested in what the underlying technology is. It could be electric, it could be petrol, it could be diesel, but that doesn't really matter to us. Those details are abstracted away because the driver experience is still just the same as whether you're driving an electric, petrol or diesel car, because the interface between different makes and models of cars is actually quite similar. Another type of abstraction that we use day to day are maps. The London Underground map is a particular example that only contains train lines, the tube stations, hub information and information on wheelchair accessibility, but doesn't include information on street network, bends in the lines, distance. It's completely out of scale. All that information, if it was added into this, would actually make the map really tricky and very difficult to read and actually make it less useful. So actually by abstracting out the details that we need to use the London Underground, so the lines, the stations and so on, is much easier for us to use and only pulling out the information that we need. So in programming, what we do is we use functions to do a lot of our abstraction. So already familiar with some functions, things like random, which is a function that creates a random number, and we're not interested in how it works, we just know that it works. When we use it, it creates a random number for us, and that is a sense of abstracting away the details of that, because we're not interested in the details of how it works. We just know that when we run it, it works for us. Another consideration when developing algorithms is we want to make them as efficient as possible. Quite often, more than one algorithm can be used to solve the same problem. So in this example, we're trying to calculate the sum of a sequence of numbers. We could use the following equation here. Okay, so n is the number that we wish to count up to. So regardless of how big or what our value we want to count up to is, this equation, we just do this equation, and the calculation in our algorithm is going to take the same amount of time. So regardless of our value of n, so regardless of how many numbers we're inputting, the time taken is just going to be constant to run this algorithm. So another way of writing this algorithm would be simply to use a for loop and then just to add up the values. The trouble is with this algorithm, even though it does exactly the same thing as the previous algorithm, is as our value of n increases, so as the value that we want to add up to gets bigger and bigger, the actual time taken for the algorithm also increases as well. So that's not ideal. So for big numbers, this algorithm is actually going to be much more inefficient than the previous algorithm.